Welcome to our comprehensive study of geomorphology. Today, we are diving into the fascinating world of mountains. We will explore how they are classified, how they form, and the incredible tectonic forces that shape our planet's surface. Let's begin by looking at the different ways geologists categorize these massive landforms. Geologists classify mountains in several ways. The first is by their period of origin. Earth has experienced a total of 9 major orogenic, or mountain-building movements throughout its long history. The 3 most recent and significant of these are the Caledonian, Hercynian, and Alpine orogenies. Let's break down the timeline of these massive geological events. The oldest mountains on Earth belong to the Precambrian period, dating back anywhere from 4.6 billion to 541 million years ago. Because they are so incredibly old, these mountains have been subjected to billions of years of upheaval, intense erosion or denudation, and metamorphosis. Today, they only survive as heavily worn residual mountains. Great examples include the Laurentian and Algonquin Mountains, located north of the St. Lawrence and Ottawa rivers. Moving forward in geological time, we have the Caledonian Mountains. These originated during the great mountain-building movements of the late Silurian and early Devonian periods, roughly 430 to 380 million years ago. If you have ever hiked the Appalachians in North America, or visited the Aravallis or Mahadeo Hills in India, you have walked on the ancient remnants of the Caledonian orogeny. Next are the Hercynian Mountains, which formed during the Upper Carboniferous to Permian periods, approximately 340 to 225 million years ago. This orogeny shaped many famous ranges across Eurasia. Examples include the Vosges and the Black Forest in Europe, the Altai and Tian Shan Mountains in Asia, and the Ural Mountains in Russia, which traditionally separate the European and Asian continents. The most recent major mountain-building event created the Alpine mountain system during the Tertiary period, between 65 and 7 million years ago. Because they are the youngest, these mountains haven't been worn down by erosion yet. They feature the loftiest peaks and the most rugged terrain on Earth. This system includes the Rockies, the Alps, the Atlas Mountains, the mighty Himalayas, and ranges radiating from the Pamir Knot, like the Pontic, Taurus, Elburz, Zagros, and Kunlun Mountains. Another way to classify mountains is by their mode of origin, specifically how tectonic forces created them. Original or tectonic mountains fall into 3 main categories. First, fold mountains, like the Himalayas and Andes, created by compressing crust. Second, block mountains, like the Vosges or India's Vindhya Range, created by massive faults. And third, volcanic mountains, or mountains of accumulation, formed by erupting magma, such as Mount Kilimanjaro, Mount Aconcagua, or Mount Fujiyama. But what happens to mountains after millions of years of weathering? They become circumerosional, relict, or residual mountains. These are the worn-down remnants of ancient fold mountains, like the Aravallis or the Urals, stripped away by denudation. Residual mountains can also form when elevated plateaus are aggressively dissected by river systems, carving deep valleys and leaving behind hills. The highlands of Scotland, Scandinavia, and the Deccan Plateau in India were formed exactly this way. We can also classify mountains simply by where they are located. On land, we have continental mountains, which are further divided into coastal and inland ranges. Coastal mountains run parallel to the edges of continents, like the Rockies, the Appalachians, and the western and eastern Ghats of India. Inland mountains, on the other hand, are situated deep within continental landmasses, such as the Himalayas, the Urals, and the Black Forest. Not all mountains are on land. We also have oceanic mountains found on continental shelves and deep ocean floors. In fact, if we measure from the absolute base on the ocean floor to the peak, the tallest mountain on Earth is not Mount Everest, but Mauna Kea. It is a dormant volcano in the Hawaiian chain that rises 4,207 meters above sea level, but a staggering 9,140 meters from the ocean floor. Its neighbor, Mauna Loa, is a similar but active volcanic mountain. Let's look closer at fold mountains. These are formed when thick layers of sedimentary rock, which have accumulated in massive crustal depressions called geosynclines, are squeezed together by tectonic compressive forces. A famous example is the ancient Tethys geosyncline, which was compressed to form the Himalayas. Because of how tectonic plates collide, fold mountains are generally concentrated right along continental margins and represent the loftiest peaks on Earth. To understand fold mountains, we must understand what a fold is in geology. When the Earth's crust is put under immense compressional stress, the rock layers, or strata, don't always break. Sometimes they bend, creating undulating, wave-like structures. The peaks of these waves, which bulge upward, are called anticlines. In an anticline, the oldest rock layers are pushed up into the core. The troughs, or downward bends, are called synclines, where the youngest rock layers are trapped in the center. Folds come in several distinct shapes based on the intensity of the compression. A symmetrical fold looks like a perfect wave, where the imaginary center line, the axial plane, is perfectly vertical. If the pressure is uneven, you get an asymmetrical fold, where the axial plane is tilted or inclined. If the compression is very strong, it creates an isoclinal fold, where the sides or limbs of the fold are squeezed so tightly they become almost parallel to the axial plane. When tectonic forces are extreme, the folding becomes even more dramatic. In an overturned fold, the axial plane is pushed over so far that the rock strata on one side are literally flipped upside down. The most extreme version is the recumbent fold. Here, the compressional force is so overwhelming that the fold collapses over on itself, resulting in an axial plane that is essentially horizontal, laying flat like a folded blanket. We categorize fold mountains by their age. Very old fold mountains are over 500 million years old. Because of relentless erosion, they have heavily rounded features and low elevations, like the Appalachians and Urals. Next are old fold mountains, formed before the Tertiary period, during the Caledonian and Hercynian orogenies. These are often called thickening relict mountains. They have medium elevations and worn top layers, perfectly exemplified by India's ancient Aravalli range. Finally, we have the alpine or young fold mountains. These originated relatively recently, during the Tertiary period, from about 66 million years ago to the present. Because they haven't had hundreds of millions of years to erode, they are characterized by highly rugged relief, imposing heights, and sharp conical peaks. The Rockies, the Andes, the Alps, and the Himalayas all belong to this spectacular youthful category. We can also classify fold mountains by their internal complexity. Simple fold mountains feature neat wavy patterns with well-developed alternating synclines and anticlines. Complex fold mountains, however, are a chaotic mix of intensely compressed rock strata. In places like the Himalayas, the forces are so violent that overfolds and recumbent folds actually snap off from their roots and are pushed hundreds of kilometers away. These detached traveling rock masses are called napes. Let's summarize the key characteristics of fold mountains. They are the youngest mountain type. Interestingly, their sedimentary rocks often contain marine fossils, proving these rocks originally formed underwater before being thrust skyward. Structurally, they span massive lengths but are relatively narrow in width, typically featuring a concave slope on one side and a convex slope on the other. You will almost always find them along continental margins where oceanic and continental plates converge. Geologically, fold mountains are highly active. Deep underground, magma often crystallizes to form massive granite intrusions within the mountain core. Because they sit on active plate boundaries, recurrent seismicity or earthquakes are very common. This friction also creates high heat flow, frequently resulting in volcanic activity, though the Himalayas are a notable exception because they formed from two continental plates colliding. Finally, these tectonic processes concentrate valuable mineral resources, making them rich in tin, copper, and gold. Now let's shift from folding to faulting. Block mountains, or fault block mountains, are created when massive areas of the Earth's crust crack and are displaced vertically or horizontally. The blocks that are pushed upward are called horsts, which form the mountains. The blocks that drop down are called grabens, which form rift valleys. Famous examples include the Great African Rift Valley and the Rhine Valley, which are grabens, and the Vosges Mountains in Europe, which are horsts. Block mountains generally fall into two visual categories based on how the crust fractured. The first type is tilted block mountains. As the name suggests, the block of land is tilted during the uplift, resulting in a mountain with one very steep cliff face and a much gentler slope on the opposite side. The second type is lifted block mountains. Here, the block is pushed straight up without tilting, creating a massive plateau-like structure with a flat top and extremely steep slopes on all sides. So, what exactly is a fault? While folding is the bending of the crust, faulting is the cracking of the crust. A fault is a planar fracture where significant displacement of rock blocks has occurred. This cracking is driven by tensile, compressive, or shearing forces from plate tectonics. Faults can be active, meaning the crust is still grinding and moving over time, which releases energy as earthquakes, or they can be inactive, meaning movement occurred in the past but has since stopped. Faults are classified by how the rock blocks move. In a strike-slip fault, also known as a transcurrent fault, the fracture is nearly vertical, and the blocks slide laterally past each other, left or right, with very little up or down movement. A special massive-scale version of this is a transform fault, which actually forms a boundary between tectonic plates. Most transform faults are hidden deep in the ocean, offsetting mid-ocean ridges in zigzag patterns, though some, like the Dead Sea Transform Fault, exist on land. Next are dip-slip faults, where the movement is primarily vertical. These come in two flavors. In a normal fault, the block resting on top of the fault plane, called the hanging wall, slides downward. This happens in areas where the crust is being pulled apart by tensile forces. Conversely, in a reverse fault, or thrust fault, the hanging wall is pushed forcefully upward over the stationary footwall. This occurs where the crust is being compressed and shortened, like at convergent plate boundaries. These faulting mechanisms create complex landforms. When tension pulls the crust apart, a central block can drop down to form a steep walled rift valley. Conversely, sometimes the surrounding land sinks while the middle block stays stationary, leaving behind a high plateau. Finally, in the real world, movements are rarely perfectly vertical or horizontal. An oblique slip fault features both dip-slip and strike-slip movements simultaneously. This complex, grinding, diagonal motion is responsible for many of the world's most disastrous earthquakes. And as we will see next, these exact same tectonic forces are intimately tied to the fiery world of volcanism. Moving right into the mechanics of the Earth's crust, let's look at volcanism. A volcano is essentially a vent or a fissure that allows pressurized material from deep within the Earth to escape. Deep underground, we have magma, which is molten rock stored in a chamber. When this magma travels up through the vent and breaches the surface, we call it lava. Volcanism is the entire phenomenon of this eruption, which often includes pyroclastics, a highly dangerous, superheated mixture of molten rock, solid fragments, gases, and ash. So what actually triggers these eruptions? It all comes down to convection currents in the mantle, creating weak zones in the crust. At divergent boundaries, where tectonic plates pull apart, magma simply rises to fill the gap at the first available opportunity. But at convergent boundaries, it's a different story. Here, a dense plate is forced underneath another, melting as it sinks. This creates highly pressurized magma that eventually violently punches its way to the surface. Occasionally, we also see volcanism at random, unusual locations. These are caused by deep mantle plumes, known as hotspots. The type of lava that erupts heavily dictates the shape and danger of a volcano. First, we have andesitic or acidic lava. This type is primarily found at convergent boundaries, where the melting subducting plate and crustal sediments mix. Because it incorporates the Earth's crust, it has a very high silica content. This high silica makes the lava highly viscous, meaning it's thick, sticky, and flows very slowly. It's light in color, has a high melting point, and tends to solidify rapidly before it can travel very far. Because andesitic lava is so thick and cools so quickly, it can actually cause a massive traffic jam right inside the volcano's vent. The lava solidifies and forms what we call a volcanic plug. With the vent blocked, the magma below continues to build intense pressure until it finally blows. This results in incredibly loud, violent explosions that throw massive chunks of rock, called volcanic bombs, into the air. A famous example of this is the volcanic plug at Mount Pelée in the Caribbean. On the opposite end of the spectrum, we have basaltic or basic lava. This lava comes directly from the mantle at divergent boundaries or hotspots, so it has much less silica. Instead, it's rich in iron and magnesium, giving it a dark color. Because it lacks silica, it is incredibly hot, around 1,000 degrees Celsius, and highly fluid. It has very low viscosity, meaning it flows out quietly and rapidly, sometimes reaching speeds of 10 to 30 miles per hour, spreading as thin sheets over vast distances. These different lavas create distinct types of volcanic mountains. First is the composite volcano, widely known as a stratovolcano. Because they are formed by that thick, slow-moving andesitic lava, the lava piles up near the vent, creating a tall, steep-sided cone. If you look inside one, you'd see alternating layers, or strata, of hardened lava, volcanic ash, and mud flows built up over thousands of years of periodic explosive eruptions. Many of the world's most famous snow-capped peaks are stratovolcanoes, like Mount Fuji, Vesuvius, and Krakatoa. Next, we have shield volcanoes. Because they are formed by that highly fluid basaltic lava we just discussed, the lava runs far away from the vent before cooling. This prevents a steep peak from forming. Instead, it creates a broad, gently sloping mountain with a massive diameter that looks like a warrior shield laid flat on the ground. These are generally quiet, non-explosive volcanoes, unless water manages to seep into the vent. The Hawaiian Islands are classic examples, featuring massive shield volcanoes like Mauna Loa and Mauna Kea. Sometimes lava doesn't even come out of a traditional mountain-shaped cone. In fissure volcanism, very thin, highly fluid magma escapes through long cracks in the Earth's surface. It flows out periodically over millions of years, spreading over incredibly vast areas. Eventually, this builds up a layered, flat surface known as a lava plateau. The Deccan Traps in India and the Siberian Traps in Russia are massive geological features formed exactly this way. We can also classify volcanoes by how often they erupt. Active volcanoes are exactly what they sound like. They erupt fairly frequently. Barren Island in the Andaman and Nicobar Islands is a great example. Then we have dormant volcanoes. These are sleeping giants. They haven't erupted in recent history and are undergoing long intervals of rest, but they still have the potential to wake up and become active again. Mount Kilimanjaro in Tanzania, with its 3 volcanic cones, is currently dormant. Finally, there are extinct or ancient volcanoes. These might have recorded eruptions in deep history, but have shown zero activity for hundreds or thousands of years, like Mount Kenya. But a volcano doesn't just switch off overnight. Before becoming fully extinct, it passes through a waning stage. During this time, the magma is cooling, and the volcano simply exhales steam and hot vapors. These gas vents are called fumaroles, and if they are heavily dominated by sulfur gases, we call them solfataras. Now let's categorize the specific types of volcanic activity, starting with exhalative volcanism. This is entirely about the discharge of gases, rather than liquid rock. The volcano emits steam, carbon dioxide, hydrogen sulfide, and various acidic fumes. You'll see this manifest on the surface as hot springs, geysers, and bubbling mud volcanoes. As we just mentioned with the waning stage, heavy exhalative activity is a strong indicator that a volcano is reaching the end of its lifespan and moving toward extinction. Next is effusive volcanism. This refers to the abundant, relatively gentle outpouring of that highly fluid basaltic lava we talked about earlier. It flows out of a vent or fissure and spreads out to solidify. Interestingly, when these massive pools of fine-grained plateau basalts cool down, they contract and fracture in highly uniform patterns, creating striking geometric columnar structures, which you can see beautifully preserved in the Deccan Traps near Mumbai. Then we have explosive volcanism, which is exactly what it sounds like. Instead of a gentle flow, the volcano violently ejects fragmented solid material, collectively known as tephra. This tephra is categorized by size. The finest, sand-sized particles are ash, which can travel through the air for thousands of kilometers. Slightly larger, gravel-sized pieces are lapilli. Then you have the heavy artillery, boulder-sized solid blocks, and volcanic bombs, which are actually lumps of molten lava that solidify before hitting the ground. Volcanism isn't just a surface phenomenon. A massive amount of it happens completely underwater, known as subaqueous volcanism. When hot lava hits the cold ocean water, it cools incredibly fast. This rapid consolidation forces the lava to form bulbous, heap-like structures that geologists call pillow lava. The extreme temperature difference also causes the outer edges of the lava to flash freeze into glassy margins, creating a fragmented volcanic rock known as hyaloclastite, which is very commonly found around Iceland. Geologists also classify eruptions based on their specific behavioral styles. The calmest of these is the Hawaiian eruption. Named after the Hawaiian Islands, this features a steady, effusive outpouring of highly fluid basaltic lava that gradually builds up those massive shield volcanoes. Very similar is the Icelandic eruption. The main difference is that instead of erupting from a central crater or lava lake, the basaltic lava in an Icelandic eruption flows out of long parallel fissures, which is what builds those vast lava plateaus. Moving up the explosive scale, we have Strombolian eruptions, named after Mount Stromboli in Italy. These are episodic, fountain-like eruptions that happen every few minutes. They're driven by large gas bubbles forming within the magma. When these bubbles reach the surface, they burst with a loud pop, throwing glowing magma into the air. A famous example currently exhibiting this behavior is Anak Krakatau in Indonesia, which emerged from the remnants of the catastrophic 1883 Krakatoa eruption and recently caused a tragic tsunami in 2018 when part of its cone collapsed. Even more intense are volcanic eruptions. In this style, the magma is highly viscous, which acts like a tight cork, making it very difficult for gases to escape. This leads to an extreme buildup of gas pressure over decades or centuries of dormancy. When it finally gives way, the result is a highly explosive eruption. It blasts a massive, dark, cauliflower-shaped cloud of tephra 5 to 10 kilometers into the sky, violently showering the surrounding landscape with volcanic bombs and massive blocks. The most devastating and massive of all are Plinian or Vesuvian eruptions. Here, dissolved volatile gases are forced up a narrow pipe-like conduit at supersonic speeds. This blasts a massive column of gas and ash up to 45 kilometers high, punching straight into the stratosphere where prevailing winds spread it globally. These are history-altering events. Mount Vesuvius destroying Pompeii in AD 79, the Mount St. Helens blast in 1980, and the colossal 1815 Mount Tambora eruption that literally lowered global temperatures were all Plinian eruptions. Plinian eruptions bring secondary hazards that are often deadlier than the explosion itself. One major hazard is a lahar, a violent, fast-moving mudflow made of volcanic debris and water that rushes down river valleys, wiping out entire settlements in minutes, as seen in the tragic 1985 Nevado del Ruiz eruption in Colombia. Additionally, these eruptions can alter the global climate. When Mount Pinatubo erupted in 1991, it pumped so much sulfuric ash into the stratosphere that it actually cooled the entire planet's temperature by 1 degree Celsius for the next 2 years. Finally, we have the Pelean eruption, named after Mount Pelée in the Caribbean. Unlike Plinian eruptions that blast straight up, a Pelean eruption is characterized by the sudden burst of a lava dome that causes a lateral or sideways blast. Instead of going skyward, a dense, superheated cloud of hot gas, ash, and lava fragments, known as a nuée ardente, avalanches directly down the slope of the mountain at terrifying speeds, destroying everything in its path. Understanding these eruptive forces perfectly sets the stage for examining the permanent scars they leave behind on the Earth's surface, which brings us to volcanic landforms. Moving right along to the landforms created by volcanic activity, we can divide these into 2 main categories based on where the magma cools. If the magma cools within the Earth's crust, it forms plutonic rocks, creating intrusive landforms. If the lava erupts and cools above the surface, it forms igneous rocks, creating extrusive landforms. Note that, generally speaking, the term igneous is often used as a catch-all for all rocks of volcanic origin. Extrusive landforms are created directly from the materials thrown out to the surface during a volcanic event. This isn't just liquid rock. The eruption expels a complex mixture, including flowing lava, fragmented pyroclastic debris, large volcanic bombs, and fine ash and dust. Additionally, a significant amount of gas is released, primarily nitrogen and sulfur compounds, along with minor amounts of chlorine, hydrogen, and argon. The openings where these materials escape are called vents. A fissure vent is a narrow, linear fracture in the Earth's surface. Through this long crack, lava typically erupts gently, without any violent explosive activity. Because the lava is usually highly fluid basalt, it spreads out over large areas, a process very common in the formation of broad shield volcanoes. In stark contrast, a conical vent is a narrow, cylindrical opening through which magma is forced out violently. This type of vent is characteristic of andesitic volcanism, where the magma is thicker and traps gases, leading to explosive eruptions that build up steep composite volcanoes, also known as stratovolcanoes. At the very top of these conical vents, you will typically find a crater. A crater is essentially an inverted, cone-shaped vent through which the magma flows. When the volcano becomes inactive, this crater is left behind as a large bowl-shaped depression. Over time, if water from rain or melting snow accumulates in this depression, it forms what we call a crater lake. Sometimes an eruption is so massive and explosive that it completely empties the magma chamber located deep below the surface. Without the magma to support the weight of the mountain above, the entire top of the volcano collapses inward into the empty chamber. This massive cauldron-like hollow is called a caldera. Just like a standard crater, a caldera can fill with water to become a massive caldera lake. It is important to distinguish between standard crater lakes and caldera lakes. Because standard craters are smaller and exist in unstable environments, their lakes are often intermittent. Caldera lakes, however, are formed in massive collapsed structures and can be enormous and long-lasting. For example, Lake Toba in Indonesia is the largest caldera lake in the world, formed by a supervolcanic eruption 75,000 years ago. Interestingly, the famous Crater Lake in Oregon is actually a caldera lake. It is also worth noting that not all crater lakes are volcanic. While many are formed by volcanic craters or calderas, a crater lake can also form in a depression created by a meteorite impact. A famous example of this is Lonar Lake in Maharashtra, India, which was created by a meteor impact during the Pleistocene epoch. Craters left behind by large artificial human explosions can also form lakes. This brings us to the concept of pseudo-volcanic features. These are topographic features on the Earth's surface that look very much like volcanic forms, such as mounds or craters, but are actually created by entirely non-volcanic processes. The main types include meteorite craters, salt plugs, and mud volcanoes. A fascinating pseudo-volcanic feature is the salt plug or salt dome. Deep underground, salt deposits under immense pressure can become ductile, meaning they behave like a thick fluid. This salt forces its way upward, piercing through the overlying brittle sedimentary rocks to create a dome-like intrusion called a diapir. Because salt is impermeable, these structures can trap hydrocarbons against their sides, forming what geologists call stratigraphic traps, which are highly sought after in oil exploration. Another pseudo-volcanic feature is the mud volcano. This is a landform created by the eruption of mud, water, and gases rather than molten rock. While some are associated with volcanic activity near subduction zones and hot springs, others are entirely non-volcanic. These non-volcanic mud domes often occur near oil fields, where volatile hydrocarbon gases, like methane, mix with mud and force their way upward to the surface. Returning to true volcanic features, let's look at the cinder cone. A cinder cone is a steep, circular, or oval-shaped hill built entirely out of loose pyroclastic fragments, such as clinkers and volcanic ash, that have piled up around a central volcanic vent. Because they are made of loose material, they have very steep sides and almost always feature a distinct bowl-shaped crater at the summit. Next is the lava dome. This is a mound-shaped protrusion that forms when highly viscous or thick magma slowly extrudes from a volcano. Because the magma is so thick and lacks enough gas or pressure to blast outward explosively, it simply oozes out and piles up around the vent, creating a steep-sided dome. However, if pressure builds up beneath this dome over time, it can lead to a massive explosion later on. We also have mid-ocean ridges, which represent the longest volcanic mountain chain on Earth, stretching for more than 70,000 kilometers across all ocean basins. The central portion of these underwater ridges experiences frequent, gentle eruptions of basaltic lava. Because this lava has less silica, it is less viscous, flowing easily to create new oceanic crust and driving the process of seafloor spreading. Now, let's shift our focus beneath the surface to intrusive or plutonic volcanic landforms. These structures are formed when magma never quite makes it to the surface, and instead cools and solidifies within the Earth's crust. Over millions of years, erosion can strip away the overlying rock, exposing these massive underground formations, which include batholiths, laccoliths, lopoliths, faccoliths, sills, and dikes. The largest of these intrusive forms are batholiths. These are massive granitic rock bodies formed by the solidification of hot magma deep inside the Earth, often forming the very core of huge mountain ranges. Related to these are laccoliths. A laccolith is a large dome-shaped intrusive body that is connected to a magma source below by a pipe-like conduit. It pushes the overlying rock layers upward into a dome shape. When magma moves horizontally and encounters a weak plane, it might settle into a saucer-shaped depression, forming what is known as a lopolith. In areas where the rock strata are folded into waves, magma can pool into lens-shaped masses. These are called faccoliths, and they are typically found at the base of downward folds called synclines or at the top of upward folds called anticlines. Finally, we have sills and dikes. Sills are near horizontal bodies of intrusive igneous rock that squeeze between existing rock layers. If they are very thin, they are simply called sheets. Dikes, on the other hand, occur when magma forces its way through vertical cracks and fissures, solidifying almost perpendicular to the ground to create a wall-like structure. Dikes are incredibly common in regions like western Maharashtra, where they acted as feeders for massive ancient eruptions. With a solid understanding of both the extrusive landforms above ground and the intrusive landforms hidden below, we are now ready to map these incredible geological features out on a global scale. Let us look at how geysers and hot springs are formed. When groundwater percolates down into porous rock, it eventually comes into contact with the intense heat of underlying hard rock or a magma chamber. This extreme heat causes the water trapped in narrow capillaries to undergo rapid expansion, converting it into high-pressure steam. When this highly pressurized steam and water find a pathway to the surface through weak zones or narrow vents, they emerge as either geysers or hot springs. Geysers are truly spectacular to witness. Along its upward path, the high-pressure steam and water accumulate in small underground reservoirs and fissures. Once the pressure builds up past a critical threshold, it violently bursts out to the surface, disrupting the water at the mouth. This is why geysers erupt in explosive pulses. You will often see a crater-like structure at the mouth, colored by silicate deposits. Almost all of the world's geysers are confined to active volcanic areas like Iceland, New Zealand, and Yellowstone National Park. Hot springs, on the other hand, behave quite differently. Instead of building up explosive pressure, the steam or high-pressure water smoothly flows to the top through a vent and condenses at the surface. This creates a continuous, gentle pool of hot water. You might notice that many hot springs are incredibly vibrant in color. This is not from the rock, but actually from different types of heat-loving cyanobacteria that thrive in the water. Unlike geysers, hot springs are found all across the world, not just in highly active volcanic zones. Volcanoes are infamous for their destructive power. Direct hazards include showers of cinders and volcanic bombs, which famously destroyed Pompeii during the eruption of Mount Vesuvius in 79 AD. In Hawaiian-type eruptions, massive lava rivers can flow down slopes and completely engulf entire cities. Another terrifying hazard is a lahar, which is a violent mud flow or debris flow. Lahars can bury cities in minutes, as seen in the tragic 1985 eruption of Nevado del Ruiz. Additionally, the sudden collapse of a lava dome can trigger violent, fast-moving flows that destroy absolutely everything in their path, like the 1902 eruption of Mount Pelée. The destruction is not limited to the immediate land. Violent eruptions, or the collapse of volcanic landforms into the ocean, can displace massive amounts of water, generating deadly tsunamis. The 1883 Krakatoa eruption and the 2018 Sundastrait collapse are prime examples. In the atmosphere, a large eruption can disperse ash over vast areas, blocking sunlight and lowering global temperatures, which historically triggered large-scale famines, such as after the 1815 Mount Tambora eruption. Furthermore, powerful winds can drive gas plumes high into the atmosphere, completely disrupting international air travel, as we saw with the Icelandic volcano in 2010. At the absolute extreme end of the scale, we have supervolcanic supereruptions. These are incredibly rare but devastating events that can cause small-scale extinctions. The sheer volume of material ejected into the atmosphere can trigger a dramatic global winter, drastically altering the Earth's climate for years. The most famous example is the Toba eruption in Indonesia, which occurred about 74,000 years ago and severely impacted global ecosystems and early human populations. Volcanoes also release hazardous gases that pose severe risks to life and property, primarily sulfur dioxide, carbon dioxide, and hydrogen fluoride. Locally, when sulfur dioxide mixes with atmospheric moisture, it leads to acid rain and severe air pollution downwind from the volcano. On a global scale, large explosive eruptions can inject tremendous volumes of sulfur aerosols straight into the stratosphere. Once there, these aerosols reflect sunlight, lowering surface temperatures, and they also promote the rapid depletion of the Earth's protective ozone layer. Despite their destructive nature, volcanoes also offer incredible benefits to the environment and human civilization. Over time, volcanism creates entirely new landforms, such as islands, plateaus, and mountains. The Deccan Traps in India are a great example of this. Furthermore, volcanic ash, dust, and the eventual weathering of volcanic rocks produce some of the most fertile soils on the planet, perfect for farms and orchards. And while the steep slopes of volcanoes might prevent extensive farming, they are excellent environments for forestry, providing highly valuable timber resources. Volcanoes are also nature's mining elevators. They bring vital mineral resources, particularly metallic ores, like copper, from deep within the Earth up to the surface, often filling gas bubble cavities in the rock. They are even responsible for precious gems. For instance, the famous kimberlite rock of South Africa, which is the primary source of diamonds, is actually the pipe of an ancient volcano. Additionally, the hardened lava rock itself is incredibly useful. It is extensively mined and crushed for use as concrete aggregate, railroad ballast, and other heavy engineering purposes. Finally, the immense heat generated by volcanic activity can be harnessed for geothermal electricity and space heating. Countries with high volcanic activity, like the USA, Japan, New Zealand, and Iceland, are major producers of this clean energy. In India, promising spots for geothermal energy include the Puga Valley in Ladakh and Manikaran in Himachal Pradesh. Beyond energy, volcanic landforms boast incredible scenic beauty. They attract massive tourist trade, with many areas preserved as national parks, such as the world-renowned Yellowstone National Park. To wrap up our discussion on volcanism, let us review the key takeaways. First, groundwater interacting with deep magma creates fascinating geothermal features like geysers and hot springs. Second, while volcanic eruptions pose severe immediate threats to life and can disrupt global climate and aviation, they are also a vital planetary process. Over the long term, volcanism provides us with incredibly fertile soils, brings essential minerals and precious gems to the surface, and offers a sustainable source of geothermal energy. Thank you for following along with this comprehensive look at the Earth's volcanic systems.